All right, so this whole chapter is about the shapes of molecules that we've been drawing with Lewis structures. And we're going to eventually tie that into certain properties that involves. So this theory of the shapes that these molecules take on is called the VSEPR theory, and it stands for valence shell electron pair repulsion. Valence shell electron, because in all of these bonds we've been doing it with valence shell electrons, because those are the electrons that are available for bonding. And it's this concept that electrons, either in lone pairs of electrons or bonded pairs, repel each other. Electrons don't like to be next to other electrons. So because of that, they will orient themselves, the atoms will orient themselves in space as far away from each other as possible to minimize repulsion. Again, because electrons don't want to be next to other electrons. So this is going to be responsible for all of these shapes that we learned today. I think there's 11 or so. So the generic concept of this is, and again, I'll go over this more. Sometimes they call this ABX. It doesn't matter. Where A is your central atom, whoever it is. B is however many things are bonded to the central atom. And E is a lone pair of electrons. And this will make more sense when we start practicing. So let's hit the ground running. Please draw carbon dioxide. So you should get something like this, all right? So this generic type is going to be A, your central atom, that would be carbon, and B, 2, because there's 1, 2 things bonded to it. All right? Now, if I were to draw this like this, you see how close these electrons are in these bonds and these bonds? Like, it wouldn't want to do this because these electrons right here repel these electrons right here. So they'd want to orient themselves as far away from each other as possible. That is this concept of the VSEPR theory. So pretty much this is as far away as they can get from each other. So what does this look like? This should look like a straight line to you, all right? Which means bond angle is half of a circle, so 180. So this is called linear. It looks like a straight line. It has 2 things bonded to the central atom, and its bond angle is 180. You are responsible for all of this information, for every single one of these that we do. Okay? You will notice when we talk about bonded pairs and lone pairs, for right now, and for this topic, we are focusing on the central atom. That is the main point of reference. So yes, oxygen does have lone pairs of electrons, but the oxygens aren't in the center, so it's not going to affect the shape for this molecule. Okay, so let's go next. Please draw BH3. So this is a molecule that has an incomplete octet, 2, 4, 6 electrons around boron. And remember, boron is an exception. It's okay. It can be stable this way. Now, the way I've drawn it is not necessarily incorrect. However, I haven't drawn it very well to shape. So look at all of this empty space up here that I'm not utilizing. Right now, I have these guys in 90-degree angles away from one another. Now, that's not going to be ideal because remember, electrons don't want to be next to other electrons. They'll want to orient themselves as far away from each other as possible. So in this instance, the best way to do that is where it kind of looks like a triangle. Okay? And what do you know about a triangle? Well, a triangle all the way around is 360 degrees. So split up 3 times is 120. 120 plus 120 plus 120 is 360. So they call this shape trigonal planar, okay? And it's considered an AB3 structure where there's a central atom, boron, and there's 3 things bonded to it, hydrogen, hydrogen, hydrogen. No lone pairs of electrons. So this thing lays flat. That's what the word planar means. And again, the bond angles are 120 degrees. Any questions on this one? It doesn't matter if the atoms are rotated, but you do want to start getting the practice of drawing them as close to the shape as you can. So how, you know how I see, I want you to start moving from doing it like this to drawing it more to shape. But again, it's going to take practice. Like, this is not a good representation of the true shape of BH3. But again, let's say you had it rotated, but it still kind of looks like a triangle. That's totally fine. Okay. Okay, now we're going to work with 3 different molecules that all have 4 electron domains. What does that mean? That means there are 4 groups of electrons around the central atom, and they're either groups of electrons in bonds or they're groups of electrons in lone pairs. It doesn't matter, just 4 groups of electrons. And remember, a lone pair is considered a group or a domain. So this is methane, so please take a second to draw it. So this tends to be the most common way we draw methane. This is how we kind of organize everything around it. Now, because we're drawing on a flat surface, this makes the most sense, but you have to remember that these molecules are not floating around on a flat surface. They're floating around in 3 dimensions of space. So the way we've drawn it, we've given it 90-degree bond angles. And that does not maximize the amount of space it could really have in 3 dimensions. Maybe on this paper it does, but not in 3 dimensions, which is where this molecule floats around in. So really, when we draw it to shape, you draw it like it has a camera on top of a tripod kind of thing. Okay? Where you kind of have this triangular base, okay? And then like a tripod sticking up on top of it, or a camera, okay? And this makes my bond angles greater than 90, which is good because if we can maximize the space, it will. The electrons don't want to be next to the other electrons, so they will orient themselves as far away as possible. And this molecule can get better than 90 degrees by utilizing all 3 dimensions of space. So this guy has a name. It's called tetrahedral, and tetra means 4 and hedral means sides or faces. So I'll draw on here for you so you can kind of see. So like this right here is the front face. One face, one side. This one off to the side is a second face. Now it's really hard to see, but there's one backwards, right, between these guys on the back. That's a third face. And then of course, there's the bottom. If you flip it upside down, that's a 4th face or a 4th side. So that's where they get the name tetrahedral. Okay, so this includes a central atom bonded 1, 2, 3, 4 times. No lone pairs yet. And the bond angle is 109.5. So this is 109.5, 109.5, 109.5, 109.5, all the way around the molecule, which is much better than 90 degrees, right? The way we drew it as kind of like a plus sign originally. So this is a better bond angle than 90 degrees, and this is what it will do in space. Any questions on tetrahedral? Okay, good question, and we're going to get to this. Multiple bonds do not affect the shape, and so having like double bonds or whatever does not affect this, because this number, this 4, is just how many things are bonded to the atom, not how many bonds there are. So like there's one hydrogen and another hydrogen and another hydrogen and another hydrogen, so that's regardless of whether there's double or triple bonds. There's still only 1, 2, 3, 4 bonded atoms. Very good question. Okay, so now we're going to take another molecule, ammonia. Oh, sorry. This is another way that they sometimes represent 3 dimensions, right? Because we're drawing on a flat surface. So this wedge would be like this atom sticking out at you. And this wedge or this dashed line would be the atom going backwards away from you. And these guys would lie in the same plane. And it's a way to try to represent 3 dimensions on a flat surface. Okay. So let's draw ammonia now. Still 4 electron domains, and we'll talk about why. So as you're drawing it, I'm going to be drawing it based on lone pairs of electrons and such. Or not lone pairs, I'm sorry, valence electrons. So again, there's 4 electron domains because there's 1, 2, 3 groups of electrons involved in bonds, and then here's your 4th in a lone pair. Still 4 groups of electrons around the central atom. Basically, we had methane before, right? It looked like this. Basically, you've taken, not methane, but you've taken this, I'll just have a central atom, okay? And you've removed a bonded pair and replaced it with a lone pair. So look, what does this look like? Well, this is definitely not drawn to shape because these electrons right here, this lone pair of electrons, will cause repulsion and push away these bonded pairs, which means it will push them down, okay? They won't be able to kind of sit flat like that because of the repulsion between the lone pairs of electrons and the bonded pairs. So really, ammonia looks more like this, where you kind of have this pyramid at the bottom. And then you go, well, what's the difference between BH3 and NH3? Because BH3, we said its shape was trigonal planar. So why isn't this going to be trigonal planar? This is a main point. Why is ammonia, and I'm telling you, it's not going to be trigonal planar. Why not? Why can't these hydrogens all lie in the same plane?
They don't sit flat because the electrons, the lone pair, pushes them down.
Very, very good. This lone pair causes the hydrogens to bend down. So we call this trigonal pyramidal, where it looks like it's a pyramid because the lone pairs on top up here cause the bonds to bend, in essence, push down. So trigonal pyramidal. And now we call this AB3 because there's a central atom, that's nitrogen. 3 things bonded to it, those are the hydrogens. And then E means a lone pair of electrons. That's what it stands for. Now I do want you to pay attention that this was before a bond, right? And the bond angles for, this was when it was tetrahedral, was 109.5 for tetrahedral. And then when the bond went away and was replaced with a lone pair, the bond angle shrunk a little bit. This is now 107.5. So here to here, here to here, here to here is 107.5. And there is a reason for this. So I do want you to kind of note this. Lone pairs of electrons cause slightly more repulsion than bonded pairs, which is why the bond angle shrinks a little bit in the presence of a lone pair instead of a bonded pair. Okay. Questions on ammonia? All right. Ooh, hold on. Oh, so the last thing I said was that lone pairs of electrons cause slightly more repulsion than bonded pairs do. Not a lot more, right? CH4 and NH3 all have 4 electron domains. Here's what CH4 looks like. They look alike, except this is a bonded pair and this is a lone pair. They both have 4 electron domains, but lone pairs cause a tiny bit more repulsion on the bonded pairs. So this was 109.5, and this lone pair causes this to be a little bit smaller at 107.5 for trigonal pyramidal, because it's a lone pair up here instead of a bonded pair. Okay. Our familiar friend, water. Let's draw it, please. So someone said if it's more repulsion, why does it have a closer angle? Well, the point is, right? So these electrons, let me draw in here. These electrons push these down further. So if it pushes them down further, they'll end up closer together, which is a shorter bond angle. Does that make sense? So if you want to look at like my hands, let's see. If you look at my hands, right? I'm sorry, I'm trying to like show you a triangle. You have like a triangle, right? Okay, you have some repulsion, but more repulsion would push these closer, decreasing the bond angle slightly because it's pushing harder on them. Pushing harder on them means shrinking them more. Yes, the angle is between the hydrogens. Yes, yes, very good. Okay, so our friend water. Whoa. Now this guy's actually drawn to shape, but I do want you to steer clear of doing it like this, which in terms of Lewis structures and how many bonds and lone pairs you have is not wrong, but this is not how water will line itself up. Now I know it seems that way, but it really won't do this. So it is going to look more like this. Now I'm going to redraw so it looks a little cleaner. So now I still have 4 electron groups around the central atom, but 2 of them are involved in bonds and 2 of them are lone pairs. And you go, well, I don't understand why you would throw these lone pairs next to these lone pairs. Aren't electrons repelling each other? And the answer is yes, but you have to remember that we're drawing on a flat surface. So really, what's happening is these lone pairs are going off different parts of the atom. So if you look at my hand again, we have oxygen in the middle, right? We have oxygen right here in the middle. There's going to be a lone pair that is over on this side of the oxygen, and then also on the back of the oxygen. And then your two hydrogens will come out in line with the oxygen. So the lone pairs aren't really shoved right next to each other. They're in the front of the molecule and then in the back of the molecule. Okay? So again, we've taken methane. We started with methane, right? And we ripped one off and we said, okay, now it's pyramidal. And now we've ripped another off, and this guy is called bent, because it kind of looks like a bent line, bent or angular. And notice that the bond angle shrinks even more between the two hydrogen atoms. And again, why is that? Oh, I guess I can't draw on this one. That's because now there's two lone pairs pushing harder on those bonds. So this bond angle goes from 107.5, like we had in trigonal pyramidal, to 104.5. I don't know why I can't draw on this one. So it's kind of like, I wish I could. If you can watch my hand on the mouse, so it's kind of like you have this is a bent line, oxygen and your two hydrogens, and then your electrons, your lone pairs of electrons are coming out this side, but then they're also over here on the back side. It's hard to represent, right, because we're drawing these on flat surfaces, but these molecules don't exist on flat surfaces. They exist in 3 dimensions. So we have a lot more ways to orient them in space. It's just harder to represent on a piece of paper. So that is bent or angular. Okay. This is where it gets a little bit more complicated. So please draw AS5. We're going to do a handful of structures that have 5 electron domains or 5 electron groups around them, meaning they have 10 electrons around them. So that would be an expanded octet. So right now we're going to, everything we've done so far had either a complete octet, except for BH3 had the incomplete. Everything we do from here on out now is going to have an expanded octet. So ASF5. So we had to utilize every single electron to bond because we had to attach 5 fluorines to it. So every single valence electron from arsenic is used in a bond. Now, this is kind of hideous looking, which is okay. It's not drawn incorrectly, but it's not drawn to shape, so I'm going to do my best to show you how this does line up. So for the true structure, you want to do trigonal planar around the arsenic. Okay, and then one will come up and one will go down. And then, of course, lone pairs, right? You have to always include lone pairs on your structures anywhere they are. You can never leave them out. Now, there's none on the central atom, but that doesn't mean you don't have to draw them on the fluorines. So now we go, well, what does this guy look like? Well, you know what one of my worst classes was? Geometry. Ugh. I was never good at all that spatial stuff. So I try to do my best to show this to you visually. Okay? So this is like a base, and then there's a pyramid going up and a pyramid going down. So they call this trigonal bipyramidal, meaning there's two pyramids. There's the top pyramid, and then there's the bottom pyramid. Okay? Now, because of this, there's actually two different types of bond angles. So because we have the trigonal planar lying flat right here, those are all 120 around the pyramid, or around the planar part. But there's also these guys. That's a 90-degree angle. That's a 90-degree angle. This is a 90-degree angle. This is a 90-degree angle. So this guy actually has two different bond angles in it, 120 and 90. And it's considered an AB5 because there's a central atom with 5 things bonded to it, 5 fluorines. Any questions? Okay, so kind of like we did with methane, where we started with methane and then we ripped a group off and replaced it with a lone pair, and then we ripped another group off and replaced it with a lone pair. We're going to do the same thing with trigonal bipyramidal. Okay, so still it's going to be 5 electron groups. It's just not all 5 of them are going to be involved in bonds. So please try to draw SEH4. Oh, shoot. Oh my gosh. Okay, so basically what we've done is we've taken something that was trigonal bipyramidal and we've replaced one of the bonded pairs with a lone pair. Okay, now what happens is if you flip, like rotate this and flip it on its side, it looks like a seesaw, like a teeter-totter, right? Teeter-totter, teeter-totter. Okay. So look, originally there was a bonded pair right here, and now it's gone. and there's just a lone pair present here. So they call this seesaw shape. Now you still have the same bond angles because look, this is still 90, this is still 90, and there's more 90s in there. But you still have a little bit of the triangle left right here. So this is also 120 between these two guys. So again, seesaw. Again, 5 groups of electrons, but now one of them is a lone pair instead of a bonded pair. Any questions about seesaw? All right. We're going to rip another one off. Please draw ICl3. Okay. So you kind of see this, right? And then you should notice that there's this electron by itself and there's this electron by itself, which really is a lone pair of electrons. You just kind of need to reorganize them so that they're next to each other. So I'm going to do that. Hmm. So I'm going to put them both on top of here. And then we'll talk about how they are in space. Okay? So in essence, we started off with trigonal bipyramidal. We ripped one off to make a seesaw. We ripped another one off, and now we have this, which is called T-shape, because that's exactly what it looks like. It looks like a T. Okay? It's a central atom bonded 3 times with 2 lone pairs of electrons. Now, remember, the bond angles is just between the chlorines right here. So the only bond angle we have now is 90 degrees. Okay? So T-shape. So where are the lone pairs, right? Because when we draw them, we look at how close they look to each other. You're like, oh, they can't be that close to each other. Electrons repel other electrons. So really you would have like a lone pair on this side over here of the molecule and then on the back side of the molecule. Okay? They'd be on opposite sides, one backwards and one forwards. And that's how they would minimize repulsion. So T-shape. And now we're going to rip off one last one. So please draw XEF2. And you're probably thinking, how is a noble gas in a compound? And you will learn that next chapter, why noble gases, some of them, have the ability to bond, which you've been told your whole life that they can't, that they're stable and they don't bond, and that is not true. Okay, so when you draw it, you should notice that I know that these guys get left out, but these two electrons will create a lone pair around xenon. So when I go to redraw it, it really looks like this. With like a lone pair right here, a lone pair here, and a lone pair here. Kind of like a triangle. Okay? But the lone pairs don't, you don't look at lone pairs for shape, you look at the molecule, which is the atoms bonded together. So what does that look like? Well, that is another form of linear. So these are lone pairs of electrons. And this is how they're oriented in space away from each other to minimize repulsion, which then makes this a 180-degree bond angle for linear. Question so far? We have a couple more to do, and then I have to go over 2 more things and we'll be finished. Possibly early, we'll see. Okay, so now we're going to do a couple, I think 3 molecules that have 6 electron domains, which means 12 electrons around the central atom, which means expanded octets. So please draw SeCl6. Okay, all electrons are being utilized. Now I'm going to just kind of redraw this the best I can to shape. So you should notice the base of this structure is a square instead of a pyramid like we had before. Okay. Now there still is a point going down, right? And one and one, going up. Okay. So when you look at this though, they're going to call this an octahedral. And you go, well, why octa? Because you know octa means 8, right? And you say, but there's 6 things attached. Why would it be called octahedral? Well, the 6 doesn't determine what the name is. The number of sides determines what the name is for this one. So let's draw on here, and I'll do my best to draw them all. Right here is a side. That's one side. Here is a second side. Here is a third side. And then I can't do it very well, but there's a back one. So that means along the top, there's 4 faces or 4 sides. Well, guess what? There's also going to be 4 upside down on the bottom. 2, 3, and then the backwards one, 4. Okay, so 4 sides on the top, 4 sides on the bottom is 8 sides or 8 faces. So it's called octahedral. Now, no lone pairs on the central atom. And then everywhere you look at this, look at the bond angle. 90, 90, 90, 90, 90. Literally everywhere you look, there's no other bond angles but 90. So octahedral. Okay. So now we're going to take octahedral, 6 electron domains, and we're going to rip an atom off and replace it with a lone pair. So please draw IF5. It's pretty ugly. Okay, so this originally was like an octahedral, right, where this side was coming up, or this part was coming up, but now there's a lone pair of electrons there instead. So it's not an octahedral. However, it does kind of still look like a pyramid, right, but with a square base. So they call this square pyramid because it stands up. So here's the base, your square base. But it stands up like a pyramid, so they call it square pyramid. And again, the bond angles between the atoms are still all 90. So 6 electron domains, but one of which has been converted from a bonded pair now to a lone pair. So AB5 and then a lone pair of electrons. Questions? Okay, one more shape. I promise. One more shape. So we're going to rip one last one off. IF4 negative. So bond everything one time. And then I have not introduced my extra electron yet, right? This is negative. So I'm going to put it right here because that will make that a lone pair. So IF4 negative. So now I've completely, so I had, right, I originally had octahedral. Then I had square pyramid. Now the pyramid part is gone, and all I have left is this square, right? And if you didn't notice, the square all lies in the same plane, so they call this square planar, okay? And again, still, the bond angles are all still 90 between the bonds. Oops, can't see that. 90, 90, 90, 90, and it lies flat. That's why they call it planar. So that is our last shape that you need to know, is square planar. 6 bonding regions or 6 bonding domains, but 4 of them are bonded pairs and 2 of the 6 are lone pairs of electrons. So a question that was asked earlier, and this is, I'm going to address it here, and you don't need to draw this, but this is the structure for carbonate. It has resonance. The double bond in here does not change the molecular shape. So this is still a central atom bonded to 3 things, AB3, and AB3 is trigonal planar. There's no lone pairs. The double bond does not affect the shape. So some kids get that mixed up. They see the double bond, they're like, oh, I don't know that shape. Well, the double bond isn't involved in determining the shape. The central atom, how many things bonded to the central atom, and lone pairs are what determine the shape. Okay? So this is trigonal planar. All right, now what happens when there's more than one central atom? Well, when there's more than one central atom, you have to focus on each central atom individually. You can't talk about them all as one shape. So for example, this is methanol, and it has 2 central atoms. This is an organic molecule. It has carbon and oxygen both as central atoms. They're both kind of in the middle. So there's a shape around carbon and there's a separate shape around oxygen. So look at carbon is bonded 1, 2, 3, 4 times. So its generic structure would be AB4. What's that? That's tetrahedral. So that means that bond angle would be 109.5. Okay? And then as a separate entity or separate shape, you have the oxygen. Well, oxygen is bonded twice with 2 lone pairs of electrons. Okay, so what's that shape? Well, that shape is bent or angular. So the bond angle around oxygen is approximately 104.5. So you can't talk about this molecule and the shape of this molecule as a whole. You have to talk about it in terms of each central atom. So on a test or something, it would be kind of like labeled, like, hey, what's the shape around this carbon? Or what's the shape around this oxygen? Because this whole thing, there's like no such thing as a shape for this whole molecule. It has different shapes in different parts of it. Any questions on that? Okay, so let's practice. I would like you to take a moment, and I'm not going to do these with you this time. I'll do them, but not right with you. So please write these down. CH3NH2, this guy's name is methylamine. And then C3H8, and then this is sulfite. So go ahead and write them down, and then I'd like you to draw them. I'd like you to identify the shapes. If there's more than one, identify the shapes, all shapes, and then the bond angles of those shapes. And I'll give you about, let's see, 2 or 3 minutes or so. So I just want to discuss these two first, and then I want to talk about sulfite with you. Both methylamine and then this is propane have 2 different, methylamine has 2 different molecular shapes because there's 2 different central atoms. So around the carbon, 1, 2, 3, 4, bonded 4 times, no lone pairs, tetrahedral. Around the nitrogen, it's 1, 2, 3 lone pairs, and 3 bonded pairs and 1 lone pair. That's trigonal pyramidal. Now be careful. Why is this not called T shape. This is very important. Why is this around the nitrogen not T shape? You're like, it looks like a T with a lone pair. T shape has to have how many lone pairs on the central atom? 2. Great. So this is not T shape. This is trigonal pyramidal. Okay. All of these carbons, 1, 2, 3, 4, carbon, 1, 2, 3, 4, carbon, 1, 2, 3, 4, are bonded 4 times. No lone pairs. So around every single carbon, it's tetrahedral, tetrahedral, tetrahedral. Any questions so far? Okay, I'm going to challenge you now, and I'm going to give you 2 minutes. I want you to draw both possible Lewis structures for sulfite. There are 2 ways to draw it correctly. So I'll give you 2 minutes. Shoot. Okay. So one way we can do this very, very easily. So this is how I drew all the valence electrons. I bonded everything at least once, and then I added my 2 electrons in. Okay. One way we can do it is this way. Create a double bond, right? This lone one and this lone one. So this is a central atom bonded 1, 2, 3 times. I don't care that this is a double bond in terms of shape. And a lone pair, so trigonal pyramidal. Okay. Now, who says you have to make that a multiple bond? The other way to do this, what if I just give that electron to the oxygen? 2, 4, 6, 8. This has an expanded octet. This does not, okay? But everything is still, either of these structures are acceptable. However, the shape is the same. 3 things bonded to the central atom and a lone pair. So this is also trigonal pyramidal. Again, both of these structures are possible. This one has an expanded octet. This one follows the octet. Any questions on those or their shapes? Okay. Last thing for today. Electron geometry and bonding and molecular geometry are slightly different. I'm not going to read this to you. What I'm going to do is I'm going to have you draw 3 structures, and we will talk about it. And then I'll talk about really what I care the most about. So please, for me, draw water, methane, and ammonia. Take a quick moment to draw water, methane, and ammonia. So ammonia is NH3. Water is H2O. And methane is CH4. All right, so this should be what you have. Methane is tetrahedral. Trigonal pyramidal is, Ammonia is trigonal, pyramidal, and water is bent. These are the shapes you've learned. For the sake of this class and generally the AP test, because I haven't seen it done differently in a long time, this is what they want. If you see methane, I want you to call it tetrahedral. If you see ammonia, I want you to call it trigonal, pyramidal. If you see water, I want you to call it bent for its shape, for its molecular shape. However, electron geometry is a thing, okay? And electron geometry doesn't take into account what it actually looks like in space. It takes into account how many groups of electrons are around it and determines its geometry based on that. So for example, methane has 1, 2, 3, 4 groups of electrons around it. We know 4 groups of electrons is called tetrahedral. Now here's the thing. Ammonia has 1, 2, 3, 4 groups of electrons around it. What does it look like? It looks like a pyramid, but its electron geometry is tetrahedral. Why? Because it has 4 groups of electrons around it, and 4 groups of electrons around it is tetrahedral electron geometry. So what does that mean for the electron geometry for water? Water has 1, 2, 3, 4 groups of electrons around it. Its electron geometry is also tetrahedral. Having taught you that, if I say what shape is water, please don't call it tetrahedral. It's bent. I have not seen them test on electron geometry for a really long time, but they also haven't gotten rid of it either. So it's fair game. So I just wanted to show it to you. Electron geometry is solely not what the molecule looks like, but how many groups of electrons are involved in the molecule. So the reason that this comes into play is look at this guy. This is sulfur dioxide. Its name is bent, and you go, well, the only bent you have ever heard of is water so far, for example, where we have 2 lone pairs on the central atom. That's the bent we know. Well, this is a different type of bent. Well, why is it bent? Well, it can't be linear because these lone pairs will push the bonds down. It'll repel them, right? So it's bent, it's just not as bent. It's like less bent. And so look at this bond angle right here, slightly less than 120. Where do you suppose that came from? Well, that came from this concept of electron geometry. There are 1, 2, 3 groups of electrons around here. Trigonal, planar for 3 groups of electrons, right? This is just not a bonded pair, it's a lone pair. And what do we know about lone pairs? They cause slightly more repulsion of the bonded pairs. So the bond angle in trigonal planar is 120. So in this version of bent, it's slightly less than 120 simply because this is a lone pair and not a bonded pair. And how did we figure that out? Well, that was determined by the concept of electron geometry. So it is used for something. It's just not commonly used for discussing actual shapes. Like if you look at this shape-wise, this looks like a bent molecule. It does not look like trigonal planar, okay, because it's missing a bonded pair. But that lone pair is still a group of electrons. Okay, I am finished with lecture today.